10 to 15% of what it should be. So future is very bright for antenna engineers. I think AC is working a bit better, but uh, I'll try to manage. You're up, right? Yeah. Okay, this is the agenda for my talk. So I'll talk about antennas, day-to-day communications. Then I give a brief introduction to satellite communication and show you some videos. I think videos are worth watching because they say a lot than the words. Basic types of antennas and the fundamentals of antennas I'll touch upon. And then I briefly talk about reflectors and phased arrays and how to design them. I think people think it's very hard to design. Actually, if you know the basics, it's very easy to design these antennas. Only thing is you have to follow some basic principles and fundamentals. So if you know them, I think my message to students is understand the basics very well. It's not how much you score or what the grade you get, but how much you understand the basics is that takes you long in your career. Ground antennas, I talk last 3-4 years. I've been working more on ground antennas and aircraft antennas. So I'll brief some of the recent developments we did. So satellite hardware and test is also very important. So testing is not easy for satellites because they're not on the ground, they're in vacuum. There is no atmosphere there. It has a lot of temperature changes. They have a lot of high power going through. There is ESD issue, electrostatic discharge. So all these things have to be taken into account. So I'll talk those things. And then some conclusions. So the message here is antennas are eyes and ears of any communication system, so you can't avoid them. So this is IEEE sponsored distinguished lecture talk. So brief thing about IEEE. So IEEE is the largest professional body in the world. So it publishes about 30% of the literature in electronics and telecommunications and electrical engineering and associated fields. It has about 175 countries. So it's almost 130 years or 140 years old. So more than 1,200 student branches. So, but most of the student branches are in the region 10, which is covering India and China. So I think student branches are very, very important to IEEE because that's where the growth is. So IEEE supports any SPC activities. So I think have more activities like this and invite other experts as well, and I think learn from them. So if you are not a student member, so please become a student member because that's very important because you can become a student member and don't stop at that point when you get a job. So don't forget about IEEE. So become a member and then senior member and then if you work well, I think you can become IEEE fellow. Not very difficult because I became one. So then if you're aged enough, like me, then you can become IEEE Life Fellow. So your number of years as a member plus your age. If it is 100, then and if you're a fellow, then you become a Life Fellow. Otherwise, you become a life member. So a lot of benefits joining IEEE. So get involved and reap the benefits of IEEE because you can network with a lot of people, experts. If you get a question and if you're stuck in your PhD, you can ask the experts and they will always help you. I think you have seen this, my journey. I think the message here is if you are not happy with, I think at any one place, you can only learn a few years. So after about 7-8 years, I get bored and you're not learning. That's time to move. So that's why I have traveled over 3 continents and 4 countries and 8 different cities, my professional career over 46 years or so. Yeah, after my master's, actually, I worked at ECL Hyderabad for 1 year. That's where I learned how to test all these big reflectors for line of sight and tropospheric scattering, how to test them. So that was a good experience before I joined IIT Madras. So, and then after that I joined LRD, but then got bored after about 8 months because everything is slow. Then I did my postdoc and moved on from there. So role of antenna in day-to-day communication, you see antennas are using on radios, on cell phones, they're used on cars, they're used on ships, and currently they're also used on satellite communication, radar systems, uh, and aircrafts and missiles everywhere. So antennas are the main part of the communication and antenna design for different types of applications. It varies, but if you are an antenna engineer, you should be able to design for any application because that comes with experience. I'm not saying that you should be able to do now, but with some experience and right attitude, you can learn and you can apply. So I'll talk about these a bit later, but I think I want to focus on two things. So this is AVAX radar, which my company built. So it has about 1,000 element phased array on top of a Boeing 707 modified 707. So, so this basically gives all early warning and control system AVAX. So you can see that antenna is not just the RF, it also involves manufacturing and mechanical engineering. So you have to work with all these people. And antenna, I would say about 50% RF, about 30% mechanical, and 20% manufacturing and test. So all these areas you need to be have some fundamental understanding. So this is another largest radio telescope in the world. 2 years back, so that is Arecibo. So that radio telescope goes from VHF to all the way to UHF and L-band. So it's about 1,000 foot in diameter. It's made out of 30,000 panels. So you can see all these panels. So they're all made into right shape and they are aligned properly. But what happened in Katrina disaster, I think about 100 or 150 panels were blown away. So now it is not functional. So the largest radio telescope now is in China. That is about 1,500 feet. But that's probably not going to be the largest for a long time. So NASA is planning to build a radio telescope, not on the surface of the Earth, but on the surface of the Moon. But the size is about 3,000 feet. So you can imagine the complexity of that structure, how you take all these, and technology will be quite different. So I'm consulting with them on antenna designs and how to do that, but it probably another 5 years, I think it will be, it will, uh, uh, it will probably finalize the design. So what is antenna engineering? So you need to have knowledge on several areas. Uh, like I said, RF systems, RF and manufacturing, mechanical engineering, testing and qualification. So all these antennas, it doesn't matter, you design, you build, and but you need to test and qualify. So what does qualification means? So qualification means actually, depending on the application, for example, the satellite, you have to make sure it works over the temperature range, it handles the high power, it doesn't have any intermodulation, passive intermodulation effects. So there are a lot of things, and it has to withstand the vibration loads of when the satellite is launched, the vibration loads are very high. So all the mechanical structures has to make sure that it can withstand. So understand the basics of antenna engineering. So I know a lot of students, I think they do a lot of mugging and try to get more marks and number one, rank number one or so. But that's, I won't suggest that to be the attitude of the student. So basically you have to understand. So I think it doesn't have to be top rank student, but you have to be strong in fundamentals, because if you have, then you can do anything you want. And at the same time, develop some extracurricular activities. Don't study all the time, but have some sports or music or dance or some other extracurricular activities. So get involved, and that in the long run, I think that's very important. So once you understand, also you have to get the knowledge of the hardware. I think antenna engineers are not scientists or researchers. At some point, you have to feel the hardware, you have to design the hardware, you have to fabricate, you have to test, and you have to go with the hardware. And when your hardware actually goes into a system, like a satellite or aircraft, and works very well, that satisfaction is more important than having 10 IEEE publications. So one antenna hardware being applied in some product is much more satisfactory than having 10 or 20 IEEE publications. So the design-wise, I think people tend to make it complicated. So always the simple is elegant. So try to make simple, and try to make it to particular applications. Any application, it has certain specifications. So try to meet the specifications, but don't overdo it. So when you make it too complicated, most of the time it doesn't work, and it's going to be more expensive, and it has problems. So try to keep it simple. So subsystem includes not just the fonts, reflectors, it has also other components, polarizers to convert linear to circular polarization and vice versa. Other mode transducers, OMT it's called, to provide the dual polarization, because most of the satellites need to increase the capacity. So they have both vertical and horizontal polarizations, or right hand and left hand circular polarization. So that way you can increase the number of channels. 2 times, and each channel means transponder channel. That's what brings the revenue. So other thing is you need to deliver the product within time and within cost. So launch cannot wait for you. If you have some problem, my design is not working, I have to redo it. So launch cannot wait. So sometimes antenna engineers have to work very uh, maybe sometimes even 24 hours a day to make it sure that you meet the on schedule, otherwise it's expensive. There are a lot of satellites, and so this is the geostationary orbit. So you can see geostationary orbit is the southern limit of Earth. That's why Earth looks so stationary compared to the satellite. So your coverage will remain stationary. But like here, you can cover deviations. So something in the satellite, it's most satellites, and then you can see vacuum here because that's Pacific Islands. So there's no population there, so you don't need satellites. So some, I think you can see multiple satellites in the same orbit location. So that is because there's different frequency bands, different applications, and some redundancy is needed. So sometimes satellites doesn't work, so you have to bring the satellite quickly down and make sure that you don't disturb the satellite service. So that was in 2001. Now there is about 1,700 to 4,000 satellites now. So what happens in future? So in another 2030, they expect about 10,000 satellites. So what's the problem? Problem is the spacing between the adjacent satellites is about 2 degrees. So that's because the ground station can distinguish adjacent satellites need to be placed at least 2 degrees apart. Then they can distinguish. So in future, how do you accommodate more satellites? So that means you have to decrease the spacing between the uh, adjacent satellites. So that's, so instead of 2 degrees, you have to go 1 degree. So that you have to have from C-band, for example, 4 and 6 gigahertz. You have to go with high frequency like 70 and 80 gigahertz. So currently we are working on that. I'll show you some slides a bit later. So these are GPS. I think I can explain these a bit later. So GPS 3, everybody uses navigation GPS actually on the mobile or on the car. So that's how important it is. So current GPS can distinguish, can provide a location accuracy of less than 100 meters. So the next generation, we want to reduce it to about 5 meters, almost like 20 times. That's mainly for military because military cannot accept 100 meters accuracy. They want to pinpoint the location so that they can take some action. Uh, this is the Asian cellular satellite. This is Echo 10 satellites for direct broadcast. This is for mobile users. So we'll talk about it more. So what is a satellite? So satellite is a link in space or relay in space. So basic purpose is to connect the users on the ground, user to user, user to ground, or ground to ground. So purpose is to provide communication between the users on the ground. So you can see the satellite at 36,000 kilometers. Radius of the Earth is 6,800 kilometers. You can see the angle plus minus 8.7 degrees covers the whole globe, at least part of the globe. To cover the globe, you need multiple satellites to cover different regions. One here, one there, minimum 3, and typically 4. So this why this is attractive? Because 1 degree covers about 6,630 kilometers on the ground, large area. So when you cover that, I think since the angles are small, your gain is pretty high. So you can get higher gain and get good communication uh, uh, signal to noise ratio. Uh, uh, and it's much cheaper than ground you can see the big towers with big antennas on top of it in different directions. So this is about 10 times more cheaper. That's why people use it. And each communication typically has two links. One is a uplink. So if you're working at C-band, so the ground actually transmits 6 gigahertz signals. So satellite receives at 6 gigahertz, down converts to 4 gigahertz and transmits back to the ground. So this is called uplink. This is called downlink. And there's a third link which is called TTMC, telemetry telecommand system. So that system is very important because it's more like low gain antennas, but that's the only communication link that works when the satellite is in the transport orbit. So if you lose that link, I think you lose the satellite. So that's how critical it is. So what is difficult in designing antennas for satellite systems? One is it says thermal. I told you that very large thermal variations. So when the sun hits the satellite, it goes up to 170 degrees C. And when the sun is on the back of the satellite, we call it night for the satellite. So it goes very cold, minus 170 degrees. So you have a total variation of about 340 degrees. So when you have such a thermal variation, some components of the antennas are very sensitive, especially filters. So filters, what happens is the passband moves around with the temperature. So that means hot and cold. So high power, most of the satellites have about 3 to 5 kilowatts of power. So when you have so much power going through small components like filters, you have to make sure the gap is large enough to handle the power. Otherwise, it multipacks and the hardware fails. PIM, passive intermodulation, is another thing. So nowadays you want to reduce the cost and you want to use same antenna for uplink and downlink or transmit and receive. So when you do that, the transmit has so many carriers, say for example 32 for a communication satellite. So these carriers beat against each other and create intermodes. So if the intermodes fall on the receive band, so receive LNA is very sensitive. So you want to make sure that your intermode levels are pretty low. So that's typical spec is minus 135 dBm. So you have to make sure that you get that sort of isolation between transmit and receive intermode. ESC, electrostatic discharge. So vacuum has no atmosphere, so it is just uh, so if you use materials like dielectrics and ceramics, so what happens is with high power, say 2 kilowatts or 5 kilowatts of power, so your charges will develop on these substrates. So over time, actually, it breaks. So and the antenna doesn't work. So in satellites, we don't use any dielectrics or ceramics. In fact, we use very pristine materials like aluminum, copper, or silver plated to reduce the losses. So everything has to be very pristine. Cross-pole, I think we need to meet about 33 dB cross-pole isolation. So that means between BP and HP or RHCP and LHCP, we need to get that cross-pole isolation. It's not 15 dB or 20 dB. So 33 dB is the spec because most of the satellites want to increase the capacity by using both polarizations. So when you have that cross-pole isolation has to be at least 33 dB. So to get that, you have to design the antenna system with 40 dB cross-pole because you can't measure that very accurately. So you have to show to the customer, including measurement uncertainty, you're meeting 33 dB cross-pole isolation. And bandwidth is also important. Signal to noise ratio, it highly depends on gain of the transmit antenna, gain of the receive antenna, because most of the other ones are system noise temperature is a negative number. SL is a space loss, 4 pi r over lambda square, both uplink and downlink. So each way it is about 210 dB. So that means 420 dB of negative number there. And 10 log BW is the bandwidth in hertz. So that's also negative. So if you want to increase the signal to noise ratio, there's a lot of pressure on antenna engineers to increase the gain of both the transmit and receive antenna. So even 0.25 or 0.3 half a dB improvement in the gain is a lot in terms of signal to the noise ratio. So you have to really optimize the gain. So this is how it looks like. The basic equation is freeze the transmission equation. I think you might have learned it very easily in the so power received, if you have two antennas, one transmitting, one receiving. So power received by the receive antenna is power transmitted by the transmitted antenna, gain of the transmit antenna, and then the losses associated with the transmit antenna. And this is the space attenuation 4 pi r over lambda square and gain of the receive antenna. So this you can manipulate in any way you want, and say for the uplink. So this is the parameter for the ground antenna. This is the parameter for the downlink. This is the parameter for the antenna. This is the parameter for the ground antenna. And this is how if you design any contoured beam or shaped beam for any country, this is how it looks like. So gain will be 32 dB to 28 dB. So same thing on the transmit side, you multiply with the power per channel, so in dB. So that becomes effective isotropic radiated power. The contours looks exactly same, except the numbers are different. Same thing for the receive antenna. So gain of the receive antenna minus system noise temperature. So that is G over T, gain to noise temperature ratio. Exactly same contour, except the numbers are smaller because it's a negative number. So some basic information about antenna radiation, directivity, polarization. So this is how antenna radiates. So to radiate, you need a signal generator, you need a transmission line, which could be a waveguide or coaxial line. And then this is a taper transition. So this is called antenna. So there are several shapes of antennas. So you need to know which antenna to use. So basic purpose of this is to provide a match to free space. So that is basically return loss. So we design with at least 25 dB return loss, not 10 dB or 15 dB. And also this defines how the patterns look on the ground or the map looks on the ground. So if you are looking, designing a satellite for India, then it has to fit very closely to the map of India. So anything excess will be loss of gain. So you have to make sure that you optimize the gain. The isotropic radiator. So this is only for reference. There's no isotropic radiator that anyone can make in real, and basically it radiates with 4 pi steradians with equal amplitude and no cross-pole. So there's no system that like that, but it's used for only reference. So its gain is 0 dB. So any directive antenna is not omnidirectional. So the narrower the angle, we know that gain is more. So depending on location and the size of the antenna, you get more directivity or less directivity. The shapes on this. So you have a medium side lobes and sorry, gain is not directivity. Some people always misuse even in publications gain and directivity. So directivity is what you compute. It's relative to the aperture. So relative to the aperture, what you compute is directivity. But what we are not interested in directivity, we are interested in gain, because gain has certain losses. So what you have to do is to maximize the gain, you have to maximize the directivity and minimize the losses. So both are important. And the polarization. So we talked about vertical, horizontal polarizations. So for satellite, it means it's a different meaning. So if you're covering a country like United States, so if the electric field vector is along north-south, it is called vertical polarization. If it is along east-west, it's called horizontal polarization. That's only definition. Whereas circular polarization, you want two both vertical and horizontal components with equal amplitude and phase quadrature. So then what happens? Your electric field vector, as it propagates through, it rotates around with speed of light. And if it rotates clockwise, it is called right-hand circular polarization. If it rotates anti-clockwise, it is called left-hand circular polarization. So sense of circular polarization is important, because two satellites didn't work because they're designing for right-hand circular polarization, but the sense was left-hand circular polarization, and ground can support only right-hand circular polarization. So both satellites, they're Japanese satellites, so they were not operational. So only other ways to, you have to modify all the ground stations to provide the left-hand circular polarization. So that was expensive. So this is how the patterns looks like. Maybe you learned in your classes from the professors. So if you have a square aperture, we know it is sin x over x type pattern. So x is kd sine theta, k is the wave number, d is the size of the aperture, theta is the angular variation. So, and whereas if you have a circular aperture, it is twice j1 x over x. This is the Bessel function of the first kind. X is Ka times sine theta, where A is the radius of the circular aperture. So the difference between the two, of course, this provides 13.2 dB side lobe levels and the narrowest beam if it is uniformly illuminated. And circular aperture provides a slightly broader beam, but lower side lobes of 17.8 dB or so. So these are theoretical numbers. So if somebody asks what is the beam width of certain circular aperture at a given frequency, you should be able to tell very quickly. So in practice, none of them works. So reason is because this is how the pattern looks like, because you don't want any side lobes. So side lobes means loss of power. For example, you're eliminating a horn with a reflector. So you want to eliminate with most of the power should be captured with the reflector, and very little power should go outside the reflector, because that means loss. So to do that, your side lobes have to be very, very low, and actually no side lobes. So this is the pattern of the corrugated horn or some of the horns we use. So it has no side lobes and no cross pole is very low. That's how you design the system. But theoretical knowledge is very important because once you know, you can you know how any practical horn behaves and patterns look like. You can calculate, or if you're in a meeting, you should be able to tell what is the beam width, what is the gain, maybe very quickly. So, and some types are two types. One is pencil beam. So that provides a narrow beam with maximum gain. So that's mostly used for military applications where you want to focus on a particular region on the ground, especially war situations. So that's mostly used in military applications. Whereas commercial applications use contoured beam or shaped beams, where you shape the to provide the beam that fits very close to the coverage on the ground. For all these, I think pointing error, because satellite is not perfect. So if your satellite is at 36,000 kilometers, if it is pointing towards Earth, I think it has certain pointing error. It moves around. So typically about 0.1 degree plus minus is the pointing error. So that's fine for most of the large beams. But if it is like a pointed beam, like a pencil beam, that is too much. So sometimes, depending on the beam width, you have to reduce the pointing error. So that is done by RF tracking. So where you can reduce the pointing error by to 0.04 or less than that. This is how the payload looks like. I don't want to go through too much, but the idea here is you receive the signal from the ground. You have input filter assembly, then you have receivers basically, and also down converters at the same time, convert from 6 gigahertz to 4 gigahertz, and some redundancy. Because always you need redundancy. If it fails, you should be able to switch to the next one. Then you have N-channel input multiplexer, then goes through TWTAs, high power amplifiers, and then you have a switch matrix to choose which one to use it. And then you have N-channel output multiplexer where you have all these 32 narrowband channels combined together and becomes a wideband channel. And you pass through the diplexer which separates transmit and receive channels and pass through the horn and the reflector. So that's basically, and how you generate the shaped beams instead of using a parabolic reflector. You shape the surface to fit the surface of any country. And to reduce the cost, you use only single horn with the proper illumination. So horn has to cover both the transmit and receive bands, or uplink and downlink. So that means your bandwidth goes up by almost 60% or even sometimes even more, 100%. So you have to design these components over wideband. This is how some of the hardware I show you, how the satellite, when it's launched in space. So your solar panels are deployed, your reflectors are deployed, spacecraft bus. So this is how it looks like, various types of antennas, mostly reflectors. And before launch, you have to shove in a small volume. That's because launch vehicle has a fairing of about 4 meters. The biggest one is Ariane, which is 5-meter fairing, but that's almost 50% more expensive. So everybody wants to fit within 4-meter fairing. So when you do that, you have to shove all the reflectors to the north and south sides of the spacecraft panel and launch it, and make sure during the launch the structures will survive the vibration loads. So this is some of the coverages what you see. This is the CONUS for direct broadcast satellite. These are the TTNC we talked about. So you have telemetry on the top and the telecommand on the top and telemetry on the bottom. So these are bicone antennas. So by choosing the right biconical angle, half angle, so you can shape the patterns for the transfer orbit operation of the satellite. So what are the, for any satellite, you need 3 components for the satellite, the ground antenna. But the third one is also very important, which is the spacecraft. So typically the launch is done in 3 stages. So first stage, it takes the satellite to about 50 miles above the ground. And then the second stage, it takes it to 100 miles above the ground and puts in the transfer orbit. So once you're in the transfer orbit, apergetic motor actually takes the satellite to any altitude you want, either GEO or MEO, medium Earth orbit, or low Earth orbit. So all three components are very important. Anything fails, I think you don't have a communication system. And these are the typical services we use. Some are scientific, some are, but for communication we use broadcast satellite service, fixed satellite service, inter-satellite service, mobile satellite service, and personal communication, which is coming up very fast. So this operates at 20 and 30 and provides very multiple beams, very narrow beams, and a large number of beams and high frequency reuse. So that's how you get high capacity. So a typical communication system has about 5 gigabits per second capacity. So with this personal communication, you get 1 terabits per second capacity, which is needed for internet and other applications. Video, play.
The advanced EHF payload, part of a system delivering unprecedented levels of assured network interconnectivity to rapidly deployable maritime, air, and ground forces, flexibly, where and when needed, immune from denial of service attacks, available in all levels of conflict. The payload puts the advanced in advanced EHF. A highly advanced digital processor serves as a switchboard in the sky, providing an order of magnitude increase in capacity versus Milstar, while supporting thousands of direct and rapidly reconfigurable flexible network connections between users on a variety of operational platforms. The processor implements advanced security and anti-jam waveform features to maintain both confidentiality and undeniable availability of U.S., international partner, and coalition networks operating at multiple security levels and within separate security domains. As with Milstar, the advanced EHF payload supports user logon and communications at lower data rates, worldwide, anytime, without prior coordination, and in the most hostile environments imaginable. And like Milstar, the payload features highly sensitive receive equipment, capable of accurately processing lower power spread spectrum signals in the EHF band, enabling low probability of detection, stealthy communications in support of special operations. The payload's fast-hopping uplink and downlink phased array antennas can flexibly cover a much wider area of the globe simultaneously with high-capacity service. While both Milstar 2 and Advanced EHF provide 6 1-degree spot beams which can be steered to anywhere in the satellite field of view via gimbal drive antennas, the Advanced EHF phased arrays support an additional 6 1-degree shareable spot beams, instantaneously steerable to any location within the satellite field of view. Operational planners have the option of allocating the capacity associated with each shareable beam among up to 4 separate regions within the satellite field of view, done on a hop-by-hop basis in milliseconds, transparent to individual users. Even with each payload's ability to deliver high-capacity coverage to upwards of 30 separate regions, there still could be a need to provide higher capacity service to isolated users outside of these regions.
Okay. So that's a video for advanced EHF satellite, which Northrop Grumman built. I think we flew about 6 satellites. So they're all working in different war situations, starting from Iraq and Kosovo and Syria and other places as well. The main thing, it works at, we talked about uplink and downlink. So downlink frequency band is 20 gigahertz and uplink is 45 gigahertz. So uplink is most important because that's, there is potential anti-jamming coming from the air, from the ground. So it should be able to adapt the beam to create a null at the location of the jammers so that the satellite is not impacted. So that's anti-jamming capability. That's at 45 gigahertz. that makes it very unique, and that's done through phased array, which I'll talk about it a bit later. So, so you need both. What you have seen is mostly reflectors. So because they are very cheap compared to phased arrays. So phased arrays you use only for military applications or applications where you need the beam flexibility. You can change the beam shape. You can adapt the beam for multiple jammers up to 8, and also you can create a spot beams and move the spot beams very easily with phased arrays.
The
So what are the types of antennas? I think with their high gain antennas, typically provided through reflectors and phased arrays. Lenses are hardly used because of the ESD. And then the about 80% or 90% is reflector-based designs, and only 10% is uh, phased arrays, because they're expensive, and you use them where, uh, where you need the adapter, the flexibility. Also, and how many bands you are covering in single satellite. So sometimes you have like this. So when you do that, each antenna you can design very nicely and meet the requirements. But when you put on the satellite, it doesn't work because satellite body is metallic, mostly aluminum, sometimes composite material. So that scatters and diffracts. And then these antennas, they have a mutual coupling. So you need to analyze all these things. So that takes about a month or two. So unless you do the spacecraft simulations, your antenna designs are not complete. So that you have to do. Reflectors, we know, most of you know about reflector antennas. It's depending on the size, the bigger the reflector, for a given frequency, you get more gain. But you also need a feed system. So feed system is not the horn eliminating the reflector. It also has other components like other mode transducers, polarizers, filters, diplexers, test couplers you need for system testing during TVAC on the ground, and waveguide interface to repeat whatever LNA or SSPA or TWTA. You need to have interfaces to that. So purpose is to provide proper illumination on the reflector. Low cross pole, we talked about 33 dB cross pole, so we design all these feeds with 38 dB cross pole isolation. Uh, 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 insertion loss has to be minimum because more loss means less power. So only other considerations as well. Different types of reflectors. I won't go. There are almost about 30 different types of reflector designs. So you have to choose what design to apply for a given applications. So there could be center-fed reflectors, offset reflectors where you minimize the blockage, and it could be a single reflector or a dual reflector system. So dual reflector is about Cassegrain and Gregorian system. So Cassegrain is where you have a subreflector which is hyperbolic, and Gregorian is where your subreflector is ellipsoid. So all these things we know the gain depends on the aperture area for a given wavelength. So that we know for 100%, but efficiency. So efficiency varies depending on the design and how much illumination taper you have, how much cross pull you have, how much other interferences you have. So like phase efficiency as well. So you need to calculate all this. Sometimes people run software and oh, I got the design and I got it. So when you look at the efficiency, it's only 40 or 30%. So at least unless the efficiency is 80%, we don't accept any design. So you have to, rule of thumb is look always the efficiency. So reflectors, offset reflector, I said we use it because it minimizes the blockage or avoids the blockage from the feed. all the rays reflected from the parabolic reflector, they go to the far field without any blockage. So that's the reason in satellites we use, and also mechanical advantages because you can deploy the reflector very easily. You can use that feed at focal point, or you can put a feed at defocus. Certain cases we need that. So once you defocus, your beam increases. So certain applications you have to do that. Uh, this is very easy. I think you can see that in my handbook on reflector antennas and feed systems. So volume 3. So this is how directivity varies with wavelength, size of the antenna and the wavelength, the d over lambda. The more, of course, the size, d over lambda, the directivity will be more, and the 3D beam it reduces. So these empirical formulas are very important, I think, to know. So large deployable mesh, we talked about mobile satellite service, where people can communicate without the ground segment. So if you have a telephone and you need to communicate with somebody on the other side via telephone, via satellite, you can do that. So that is called mobile satellite service. So typically done under L-band and for example, need a large reflector to get the proper gain. So conventional reflectors cannot because of the limited space you have before launch 4-meter fairing. So you have to use very large reflector like 12 meters and even 25 meters sometimes. So that is done through mesh reflector technology. So you have a mesh like this. You can see the close. It has 10 openings per inch. So this mesh material is about diameter is about 1 mil, 0.001 inch diameter, and it's a gold moly mesh. This is very high tensile strength, and also it's very lightweight, something like 0.025 kilograms per meter square. So that's very lightweight. There's two companies which make this in the world, I would say. One is Northrop Grumman. So my company, which makes like has a front mesh and a back mesh to support it, and connected by truss type structures. And you can fold that into, if it is too big, you can fold into smaller volume, and you can have multiple folds as well. Harris also is makes very good mesh reflectors, another company. So it doesn't have the back mesh, but it has a truss type structure to support the front mesh and the radial ribs as well. So both are very valid. And openings per inch, I think 10 is okay at low frequency. But now I think people want to gain for personal communication. They want to get very narrow beams. So they have to use mesh reflectors with 6 meters or larger. So when you do that, 10 openings per inch gives more loss. So you have to go with 40 openings per inch to minimize the reflection losses. Some video there. So this is mainly to show how the mechanical structure is very important for this type of. This is a NASA soil moisture active passive program. So we build the antenna and they build the satellite, NASA. So you can see once in space, the solar panels are deployed. So this is actual antenna, mesh reflector, 6 meters in size. So this is the mechanical boom assembly where it deploys the reflector. So once it deploys, then it now unfolds into a parabolic mesh, just like an umbrella. And you have to do that very slowly. So this satellite is a low Earth orbit satellite, which is at 680 kilometers above the ground. Main purpose is to measure the depletion of the icebergs in the northern hemisphere and also soil moisture. So it rotates about 35 conical angle, 35-degree conical angle at 15 RPM, so that it creates a swath of 1,000 kilometers on the ground. So as it moves along the ground in the North Pole, so it creates a 1,000 kilometers long swath, and based on the return signal, monitored over a number of years, you can see how icebergs are decaying, at what rate they're decaying, and then you take an action. And also soil moisture, how it is changing. So now we come back to phase arrays. I told you that phase array is very easy to design. It's not very difficult. People think it's very difficult, and only thing you have to know is some basic facts. So grid, I think, is very important. Whether a regular square grid or hexagon we use, some people only provide grid, but its unit cell is hexagon. So what is important is spacing, inter-element spacing between the elements. So use more elements, you get more directivity. And depending on the gain requirement, you choose the number of elements. So for square, I think you get this. So theta sm is the maximum scan angle because all phase arrays have to scan the beams. So if it is a global geostationary satellite, it has to scan over the complete Earth, which is plus minus 8.7 degrees. So you need to minimize the scan losses. At the same time, you want to minimize the grading lobes within the coverage. So people use this mostly for radar applications because you don't want any grading lobes in the visible space, that is plus minus 90 degrees, because you don't want that. You have to keep the elements very close, lambda by 2 spacing. So that's good. But if you go, that means it has a lot of elements to get certain gain. So here actually for satellites, we want grading lobes. It's not like we don't want grading lobes. We want grading lobes, but we want the grading lobes to be slightly away from the coverage region. If it is 8.7, we design the phase array with 12-degree grading lobes. So why we do that? Because you can increase the spacing between inter-element adjacent elements. Instead of half lambda, we use about 3.5 lambda or so. So that means a ratio of 7. So square that about 49. So you can reduce the number of elements by a factor of 50 compared to 0.5 lambda spacing. So the cost of the phase array goes with the number of elements because you need everything you need the cost to do that. So that's and also we use hexagonal lattice because it reduces the number of elements because you can increase the inter-element spacing by about 15% compared to the square grid. So these are the requirements and these are the design parameters. So once you know what is the gain, you can choose the select the number of elements. And the basic thing you have to do is how to design the element. So these are some phase arrays. So the advanced EHF video you have seen, the uplink phase array has about 400 elements. So that is 400 horns. So each is about 3.3 wavelengths in size. And you can see protected aperture on the top. That is mainly for thermal because it sees very high temperature. Need to protect the sensitive components. So it's a RF, very minimal RF loss. It's almost RF transparent. And then you can see it's basically down converted to C-band and beams are formed. And then you have heat pipes actually. So a lot of heat is generated. So it's LNA. So you need to dump the heat into spacecraft panels. So that's a lot of mechanical design. And then you basically go into baseband, digital processor, where you can sort of process the beams and move the beams, adapt the beams anywhere you want. So that's all complex system. So this costs roughly, each phase array costs about $20 million to build. And there are other phase arrays which are used for ultra wideband UWB, where you need wide bandwidth. So these are bow tie type elements. So you can see bow tie elements, both horizontal and vertical. And stacked patch, you can get the bandwidth around 2.5 to 1. These you can get bandwidth up to 10 to 1 bandwidth. So this is a conical notch element. You get about 16 to 1 bandwidth. So we call it bandwidth. It's a ratio of the highest frequency to the lowest frequency. So you can't call it percentage bandwidth. You basically have to call it bandwidth ratio. So I talked about this pattern. So you can see how it performs. So mainly I want to show the return loss. We design the whole feed system, including all the components with the 28 dB return loss and on the receive 32 dB return loss. So everything is transmitted very, reflected power is very low. And isolation is pretty high, 25 dB between right hand and left hand circular polarization. Peak power is 10 kilowatts. And then passive intermodulation is about minus 140 dBm. Taper is about 20 dB on the reflector. So you see the crosspole level about 38 dB. So that's enough to meet the 33 dB crosspole. And insertion loss, you can see whole feed assembly is only 0.15 dB, including filters. And the receive side, it's only 0.05 dB. That's how you want to optimize, minimize the insertion loss. So another video. So
The V2 Spirit. The V2 was originally intended to carry nuclear bombs deep into Soviet territory if the Cold War had ever turned hot. Its shape, paired with the plane's stealth systems, would enable it to be undetected by Soviet radars. The V2's long range meant it could fly deep into enemy territory and return home. With the collapse of the Soviet Union and the end of the Cold War, the V2 has been used as a conventional bomber. It made its combat debut during the Kosovo War in 1999, and has since flown sorties in Afghanistan, Iraq, and Libya. More recently, the V2 has been placed in bases in the Pacific as part of a strategy to deal with potential threats from North Korea. Here's why it's one of the most feared aircraft in the world. The V2 bomber was shown to the public for the first time in 1988, just before the end of the Cold War. Its stealth capabilities were virtually unmatched. The V2 can carry 16 2,400 pounds B-83 nuclear bombs, but its official limit of 40,000 pounds of ordnance means it can carry a massive amount of precision-guided munitions. The V2 has a max range of 6,900 miles on a single tank, but aerial refueling can keep the bomber up indefinitely. On one bombing mission, two V2s flew a 34-hour round-trip mission from Missouri to Libya, and were refueled in the air 15 times. Each of the current 20 V2s in service are named after estates. Here, the Spirit of New York can be seen at the British Royal International Air Tattoo in July of 2012. The V2 is a flying wing aircraft, so it has no fuselage or tail. This means it has low drag, high structural efficiency, and generates more lift than other fixed-wing aircraft. The V2's max speed is Mach 0.95, or 630 miles per hour.
So you see the B2 bomber that's made by Northrop Grumman, and you don't see any antennas there, but there are about 50 different types of antennas. And the reason you don't see any of them is because it has to be stealthy, so it cannot be detected by the ground radars. That's the reason. But all these 50 different antenna types have different applications. So when you put all these 50 antennas at different frequencies, different places, so they interact with each other. So that's where I think you have to analyze very carefully and see the interaction between antennas and is different because it has to be, it absorbs a lot of RF signals. So it has frequency selection as well. And we finished the design work 2 months back, and the production starts. This is a 30-year program, costs about $100 billion. So biggest contract given by the Air Force to any US contractors. So a lot of work there, a lot of lot of people we need, and I think a lot of development going on.
The B2
So now I switch to ground antennas. The last 3 years, I've been working a lot on ground antennas, mainly for the soldiers on the ground, where the soldiers go with a man pack in a battlefield situation. So the constraints are a bit different there, because the soldier can carry only limited amount of mass with him. So antennas have to be very lightweight, and it has to be deployable as well to provide the function. So a typical soldier on the ground has more than 16 or 18 different antennas for a different communication link. So all these are very important, and how you pack them very compact in size and low cost and low weight. So you can see the soldier on the ground trying to communicate with the local units, headquarters, and also to different aircrafts. So as to distinguish between foe aircraft and the friendly aircraft, so that he can pass the message to the headquarters, and also has to communicate with satellites. So this is the one we made recently, about 3 months back. Completed the design and completed the testing and delivered to the customer. Before, there used to be 4 phase arrays. So now all the one for KU transmit, KU receive, K-band receive, and K-band transmit. So all the 4 bands, 4 phase arrays, they're expensive and heavy, and they dissipate a lot of power. So we wanted to combine, and the way to do is we want to make it lightweight as well and low cost. So the lightweight we make by using petals on the reflector, which is Rexolite material, and you can 3D print them very easily, and then you metal coat them. And then you have a subreflector in the feed. So feed is also 3D manufactured. So this is a quadridged horn illuminating a subreflector. And then you have a gimbal system. So typically for satellite, gimbals cost about 1.5 million, 2-axis gimbal. Whereas here we want to reduce the cost. So we buy a COTS item, which is used gimbals for the cameras. So the company supplies around $500 per unit. So we buy that. So it provides elevation coverage of plus minus 90 and azimuth coverage of 360. So which is good. And then you need a tripod so that the soldier can mount it to provide the communication on the move and the communication at the halt. So this is a graphite, lightweight graphite. This is also COTS item, costs about $150. So everything is cheap. So these petals could be replaced. So you can see all the 6 petals. They can be folded and put in a box, and soldier can carry. So again, I think we sort of, our spec was about 20 pounds. We made it in 10 pounds. So it's very good. And cost is very low as well. So it is currently going through field tests by the soldiers. And once the field testing is complete, then I think we'll get thousands of units built in the next couple of years. So we have a patent, and we also have a paper coming up soon in the IEEE transactions. This is another antenna for the ground where you need flexibility. So this is mostly done at K-band, and also actually once I think we provided the wideband capability, then the customer said, why don't you provide communication at KU band, also Ka band. So this is more than octave bandwidth. So this is inverted F antenna. So with a radome, you can see on the top. So difficulty with that is you need to provide almost 4 times the radiance coverage, just like Omni, but over 85% of the coverage. And then the soldier, when he's lying on the battlefield, so it has to be folded. You can see here. And the antenna, and then actually this is the support struts, this is the handle, and these are the 2 stops where it sort of folds like this. And you have 2 clips actually. These are 3D printed as well. This is 3D printed, 3D printed. This is bought, parts item. So this is the only thing we make. And then there is RF cable actually going through the tube and connected at the bottom, coaxial connector. So two configurations, so folded and unfolded, same antenna. So when the soldier is standing, it has to go about another 13 inches from here higher, so that soldier's head will get radiation. So we need to keep certain distance. So this is actually coming in October issue of IEEE transactions on antennas and propagation. And also we have US patent pending on this technology. You can see the patents here. Our gain was about -8 dBi. I think we are meeting with a lot of margin. And the other thing is when you have 4 pi sterdians, imagine here, this has to be very low scattering. So the size is, you have to minimize the size. You have to choose the materials where it doesn't scatter. You cannot use metals. So that's why you use mostly dielectric type materials. Yeah. And this is another applications where maritime, used for maritime communications, where you have different waveforms you need to propagate through GSM, wedge, and other types of waveforms. And the bandwidth is very important. So you have to get a 60:1 bandwidth ratio. So how do you get that? Any UWB antenna cannot give you more than 20:1 bandwidth ratio. So to do that, we have segmented antenna design in a compact volume. So we have to do it over 25-inch by 25-inch size and certain mass. And so we did that in 19-inch by 19-inch. So it has basically 3 antennas. One low frequency, 1 to 8 gigahertz, covered by the quad-digit horns. These are quartz item available. And then medium band antenna is a horn, high gain horn. And then high band is a reflector antenna with a sub reflector. This is a 15-inch in size. This is about 7 inches or 6 inches. These are small. And it has to be mounted on a gimbal, so you need to provide complete coverage, both elevation and azimuth, and a support structure to mount on the field. So this is how the gain looks like. So low band, mid band, and high band. So what happens is on the mid band, I think customer wanted 2 dB more gain. So here there's no space to grow the horn to provide the more gain. And even if you grow the aperture of the horn, you won't get more gain because phase errors take over. So phase errors basically drop the gain. So what we did is we attached a lens on top of it, a spherical lens. Oh, by the way, if you want to make a real UWB antenna, you need about 10,000 elements to meet the gain requirements. So that's almost impossible. So here we built a dielectric lens on the top, spherical lens, so which is, you can see the grooves. The grooves are for matching. So that provides extra gain what we wanted. So what lens is doing is it converts the quadratic phase error into planar phase front. So that's what you get the gain increase. So this is another program we are still working on for advanced missile systems. I think currently US has Minute Maid, which is 30 years old technology. Now they want to develop improved missile technology with better positional accuracy and better performance. This is typical phase pattern. So on the missile you have a ring type antenna. So missile is, the body is about 120 inches long and 56 inches in diameter. So antennas are, we call it ring antennas. So before they used to have only 2 patches which are 180 degrees located around the periphery of the missile body. So that gives this pattern. So now they want phasor spec is about 25 degrees plus minus. Now they want the phasor to be controlled very well within 1.5 degrees total. So that means plus minus 0.75. So to do that, we have to come up with a new design. So that's the design. So basic, it operates at two GPS frequencies, L1, L2, and S is basically the S band is for TTN's application. So to meet that plus minus 0.75, even measurements, you don't have any measurement facility, the near field or far field, to get that range. When we talk to the people, they said the best they can give is about 5 degrees. So we have to work with them and make sure that we get the phase accuracy within zero point 0.2 or 0.3 degrees. And then simulations. Simulations are not accurate as well when you talk about plus minus 0.75. So we talked to HFSS, and initially they said they can give only 2 degrees accuracy. But then we force them to increase the mesh size, make it more dense to get the accuracies. And currently, I think we're getting about 0.2 degree phase inaccuracies. And design also has to be very tight. So you have to make sure your design can meet those accuracies. So to do that, we have RF fences. So you can see. So that is mainly to isolate the 3 different frequency bands. And also we have, this is divided into 6 rings around the periphery. So each ring has about 8 elements, so total 48 elements. So each one is a metallic strip, but it is fed at 8 different and it's a half-inch thickness. So we made it within 0.35 inch thick. And you can see when you do that, the phase variation is very minimal. You can see 301 almost plus minus 0.1, 0.15 at this frequency. So this has to work over a large elevation angle covering 25 degrees to 155. Only thing is it doesn't need to provide any coverage when along the nose cone or tail of the missile. But 90 degrees, you can see the phase error you get is 294.5 almost to 295. So it's very low. So we meet the spec. So we have finished the design, and we have another 9 months to make engineering model to build the test and show the customer that we meet the requirements. This is the ground antenna. I think I'm almost close, another 10 minutes or so. This is the current Air Force has about 150 ground antennas, most of them for different applications. Most of them work at Ka band and S band. L band, L and S band is one. So it's a prime focus system, and the Ka band is dual reflector with a sub reflector, and then separated by FSS, frequency selective surface. So frequency selective surface reflects the Ka band signals and transmits the L and S band signals. So now they want to cover 9 more different frequency bands. And how do you do that with this system? You cannot do FSS, cannot isolate 9 different frequencies, and you cannot put more feeds. So we removed the FSS, we removed the struts because they're lossy, and then we went into a coaxial design where you have multiple coaxial. We have 2 coaxial rings around the central element, and use the main reflector so that cost is low. So basically, we cut the support struts and then built a new feed, and currently it's being tested, and I think it will be the Air Force ground antennas with the new system. Talked about high frequency W and V band. So in future, so currently we have an experimental satellite launched last year. So because nobody knows at this frequency what is that atmospheric attenuation and what is the cross-pole discrimination. So those two parameters are very important because people have measured at C-band, A-band, and conventional K-band, but nobody knows it is frequency. So there are 5 ground stations around Konus, Air Force stations, so you can see them. And we kept this experimental antenna very simple, basically 2 large horns located around north-south, so that they provide the Konus is more like 2-to-1 ellipticity. So along east-west, it's 2 times more than north-south. So with this, you make a narrow beam on the north-south and broader beam on the east-west. So currently, I think it's they're testing it, and it will continue another 5 years. So idea is to test it to different weather conditions. When it rains very heavily in Florida, so we have a ground site there, and then East Coast also rains moderately, and then where I live on the West Coast, it doesn't rain at all. So in New Mexico as well, it's a dry. So that's one ground station is there. And Colorado Springs, it snows a lot, so there is another ground site as well. Multiple beam antennas, that's where we use for personal communication. So how do you get the high data rates from 5 gigabits per second to 1 terabits per second? So use more beams. So instead of covering the Konus with one beam and putting all the spectrum into one beam, you divide that into spread over 60 beams, small beams. They provide high gain, and then you divide the spectrum into 4 sub-channels. So if it is 1 gigahertz spectrum, you divide into 250 megahertz. So use the channel 1 on alternate beams, 1, 3, 5, channel 2 on 2, 4, channel 3 and 10, 12, and channel 4 and 11, 13, etc. So when you do that, 60 beams with 4 channels, you get a frequency reuse of 16 over 4, which is 15. So instead of 1 gigahertz, you get 15 gigahertz spectrum, so which is needed. And because the beam size is small, you get more gain. Instead of 40, 60, 50, sorry, instead of what is that? Instead of 31 dBi, you get 46 dBi, about 15 dB more increase. That means both up and down link is about 30 dB more gain. So with that, you can get very high capacity, and also you can make the ground antenna smaller. Instead of, you don't need a 30 meter antenna. You can do with 1 meter or 1.5 meter antenna. This is another for DBS. Here the complexity is beams are not uniform. I think when the customer came to, I was working at Boeing 1999. They want to cover about, whole United States is divided into 216 designated market areas based on the population density. So New York is number 1, Los Angeles is number 2, Chicago is number 3, etc. So they wanted to cover only 100 DMAs. So before they came to us, they were working with another 2 contractors, and they were trying to simulate, and it's not easy because the DMAs are not same size, they're different size, they have different attenuations. So you provide the more gain on the East Coast, less gain on the West Coast. So, and then how you allocate the channels to each DMA, that's very complex. So they tried about 3 months, and they said that they can cover only 50 DMAs. Then they came to us, and then I said, then I was asked to look into that. I said, if you go through simulations like Picra or any other software, you can take months and months. There's nothing, you cannot design it. So we have other ideas. So I believe in complex So, but you need to same color beams, you need to isolate them. So you need to provide copolar isolation, and how you design uh, these small and big beams. So you have to vary different horn sizes. By varying the larger horn, if you use, your beam becomes on the ground larger. So sometimes if it is too large, like this beam, you have to use multiple horns, 3 horns, fed with a BFN, high level BFN. So these are the tricks I think one can use. This is the next generation GPS. I told you the next generation GPS want to reduce uh, improve the accuracy on the ground by a big factor. So to do that, you need accuracy depends actually on the group delay. So group delay is basically variation of the phase with the frequency. So that means your phase center at different frequencies has to be very stable. So that's we come up with a new element like this, lightweight, at the same time provides very, and it creates different beams. You can see spot beams very high again, and this is Earth coverage beam. Basically, this is a medium Earth orbit satellite at about 22,000 kilometers. So this is how the gain is here and the ERP is here. So basically, you share all the amplifiers between all the channels, L1, L2, and L5. So it's fed through digital beamforming network. This is the array. And then it has UHF crosslink as well, because this is a global constellation. So the satellites have to talk to each other. So that is provided through crosslink, UHF crosslink. This is a development which we did with Florida International University. This is probably futuristic. So anyway, it's, can you run? So basically it has 3 states. So it's a helix design. So depending on the frequency, yeah, leave it there. Just play it. Take some time. So depending on the frequency, yeah, leave it there. Don't move. So what it does is basically this helix goes up and down. This is called origami structure. So basically it's how you fold the paper and make the antenna. So, and not only the helix is reconfigurable, but the ground plane is also reconfigurable. So this has the 3 states, starting at 20 gigahertz, 30 gigahertz, and 44.5 gigahertz. So 44.5 is a small helix. So I think it's working well, but not there to propose as a product yet, because it has to be qualified, and it's a small R&D work we did with Florida International University. These are scientific missions. Mostly NASA does that, and we do also, like SMAP. So various missions. This is Galileo. This is a 4.5 mesh reflector, which is built by Harris. So they launched it, and what happened is the reflector didn't deploy and got stuck in the middle. So what they have to do is they have to take it to the sun, very close to the sun, heat it up, and then it deployed. So by the time it came back, very little fuel is left, and the life of the satellite had gone down to 6 months. So accidents happen. So qualification test, I told you, is very important. It's not the patent test. You have to qualify over thermal range, thermal vacuum test we call it, polarization test, bench test, PIM test, high power test, and thermal vacuum test. These are all electrical tests. And then mechanically, you have to make sure it vibration, like it meets the vibration level, sine vibration typically, or random vibration, acoustic. So there's a lot of acoustic loads as well. And then alignment. So you have to make sure the antenna is aligned such that it sees right point on the earth. so it doesn't move. So those checks you have to do. And at system level, spacecraft level, we do TVAC again, EMI, EMC, and final pattern test as well. And this is how the test sequence goes. So it goes through health checks, temperature check, uh, ambient uh, uh, feed patterns, random vibe, health checks. Health checks is basically what checks before and after. Uh, you see any big difference on this or something wrong and move the testing to the next near field range, compact range, and quick chambers, and bistatic range to measure the material properties of frequency selective surfaces and uh, and thermal shields as well. So this is the observation I have. Question is whether the academics are providing the right training to engineers. So this is mainly for years. And we get students from a lot of universities, even big universities like UCLA, USA, but they're not up to the mark. I think they come and even after 1 year, I think they're not working at the right level what we want. So then we sort of government also realized that, and they called mentor prodigy program, where the university provides the interns, and then we have a small company that works with us, and then it's a three-way, Northrop Grumman, university, and so we take them as interns, train them for 2 or 3 years, and once they finish the graduation, we hire them. So that's the whole purpose we have on. And every year we hire 2 people, and this has been very successful actually. Instead of hiring them directly, I think we give the right training before, and then when they graduate, they're ready to work with universities. So I think so. Most of the universities they do HFSS, CST, FICO, which is good. But real world, I think you have nobody, at least in India, I see working on reflectors and horns. I told to ISRO, Rajiv Jyoti and few other people, and they are actually collaborating with universities now. So, and then there's various different softwares, Cobra, this is for aircraft, CST, Savant, Spot 3D, that is for multi-paction analysis. Hardware, I think you typically use patches, slots, reflector arrays. And in real world, you use horns, reflectors, and different types of antennas for space, ground, and air. So you guys have a lot of talent. I mean, I see that antenna engineers in India are much more capable than what we get in antenna engineers in US. So I think they have a lot of motivation, and they're willing to learn, and they're willing to develop. So that's very good. So we also have a lot of companies here, ISRO, DRDO, Raman Research Labs, uh, observatories, and a lot of other places, Samir, TFRL. So I think if you do learn good and try to focus on it, I think it will be good for you, for your career, whether you want to go into academics or you want to go into industry. So the university-industry relation is very important. I think it will, to a certain extent, remedy the situation what we have currently. So this is a team we have with a small company in Colorado, and then professor at uh, 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 Cal State, Los Angeles, and then his two students actually. So very development and communications. I think that's very important to apply for any engineering problems and develop concepts and out-of-box ideas. Sometimes people tend to use, oh, previously I've used this design. I'll try to use the same design. Application is different, so that doesn't work. So always try to think outside the box and come up with new designs. And sometimes in the process, if you fail sometimes, so that's okay. Don't be afraid to fail. Of course, you cannot fail too many times. Otherwise, you don't have a job. So failing once is fine, but learn from the mistakes. And especially in satellite business, you cannot fail. Acquire critical skills. I think always look into hardware. So don't do paper designs, and paper designs will never fly. So you have always convert the paper designs into hardware. And also work with passion. So it makes a big difference because every day you go to work or you come to the university, you want to do or learn something new. So don't just waste your time, and you don't need to work hard, but you have to work smart. So I mean, always I tell my uh, employees working in the group, don't work too hard, don't bring home to work, and don't take work home. So I isolate both, and then I think you will be very happy, and you'll have very happy wife, very happy family. So no problem. So whereas if you start taking work home, I think a lot of problems will come. So. And then time management is important. So when you are working, make sure that every minute you work, I think, is fruitful. Of course, you need some breaks, but whatever you work, I think be focused on the work and don't miss time. So you need to develop other activities also, like social activities and meet friends. Don't do excess. So innovation should be daily routine of engineers. So this is a quote from Steve Jobs. Innovation distinguishes leaders from followers. So I think you want to follow to a certain extent your process and learn and your mentors as much as possible, but don't continue to follow them. At some point, you have to break the tie and you become the leader. So that's how you grow. So last one is advertisement for VAM's symposium. I think Professor Karthikeyan is an executive committee, and I hope he'll send a lot of students to VAM's conference. So the travel grants are they're giving for free. So if you're willing to travel, we'll pay the train fares. Accommodation is free, food is free. We just have to pay minimal registration fee. Something like, I don't know, how much is it? 2K or something? 2,000, 3,000. So free accommodation in the hostels. So that's how you learn, meet other people, go to conferences, and if you are sitting in one place and do, that's your limit. But if you go outside, I think world is big, and you can interact with other people, other students, and other professors as well. So try to do that. But I hope Professor Karthikeyan is coming, but I know his limitations, but I know Nrsimha Pradhan is coming. But so if anybody of you interested, I think let your professor know, and we can arrange the travel grants for you. Okay, that's all my talk. And any questions? So far, nobody asked any questions. Supposed to be interactive.
So take from participants.
Wish I just ask.
Sir, thank you for your session. And I have two questions, sir. Like, what is the antenna used for GPS applications? Sir? Like omnidirectional antenna or single band, like only one direction?
It depends. I think both are used. The one used really for GPS is a highly directive antenna. So it's, you have seen the helices before, number of helices. The other one I showed next generation is 37 element radiating element array. So they're waveguide, but you can see the perforations, that is only to minimize the mass. So they have also omni type antenna, which is for crosslink. You have seen the UHF around the L-band antenna ring. So that is to provide the cross-link between the satellites. So both are used, but the main emphasis on the L-band antenna, which is a directive antenna. So it provides a spot beam as well as the earth coverage beams, and it can vary the power going through each of those beams because power is shared by the amplifiers. So you can put more power in spot beams, less power in earth coverage beam, or vice versa.
Now, one more question is like general one, sir. Is there any situation that you have encountered that the simulation or the software of the device is worked properly, but after fabrication or after designing it physically, it did not work properly, or it is like fail? Is there any situation that you have encountered, and what are the like parameters or the controls you have to take care to avoid the situation?
Yeah, so actually, machine down, you know how much is the error you get, 2 mil error or 3 mil error. So take that into account and do the simulations and take the material properties properly. And then nowadays, I think initially people used to sort of see big differences. Now we don't need the event to measure because this is basically designed to perform. So basically, whatever you do, if you take all these precautions into account, you can you make it, and then you test it, you exactly meet the what you simulate. So and simulations also, sometimes you have to test by two different softwares like maybe CST and HFSS. Sometimes HFSS might give wrong results, and you have to verify with CST or FICO. So you have to be careful and then make sure that material properties are you take into account and the tolerances you take into account. And when you do it properly, I think you don't need to measure, but of course you have to measure it to prove to the customer that it works. So some precaution there to take. Good question.
Thank you, sir. That's it.
Sir, thank you for your session. Sir, I have a question, but it is not an antenna. In the satellite payload, can you give me some significance of the filters that is used in the input-output multiplexers of the satellite payload?
Yeah, that's a good question. Nowadays, actually, filters we are implementing in antenna itself as part of the antenna. But of course, when you have a communication system where you have output muxes, so you have 32 channels each 5 megahertz and covering certain bandwidth. So they are mostly high Q dielectric resonator filters because the gap between the channels is very small. So they have to be high Q to provide the isolation between the channels. So those are mostly dielectric type resonator filters with high Q. Each one has maybe 8 pole or 10 pole depending on the isolation you need. So it's very complex. So input is not that stringent because there's no amplification. So any output filter is, you have to be low loss at the same time, the performance is important. So apart from input-output mux filters, you have also filters on the antenna side. So antenna has several filters because FSS, you have to follow the FSS regulations. So you need to suppress the radio astronomy bands at different frequencies. For example, 10 gigahertz, 35 gigahertz. So you have to make sure that you filter those, and also you uh, provide the rejection for other frequency bands. For example, if you use same antenna between transmit receive, so we have to isolate and you have to make a diplexer with a common port and receive reject filter and transmit reject filter. So that's called diplexer. So a lot of filtering is very important. So both at payload level and antenna level as well. So repeater has the filters, antenna has filters. So you sort of choose. We try to mix most of the filtering in antenna because it's low loss, whereas any at the repeater level, mostly it's strip line or microstrip type filters, especially input filters. So they are more lossy.
Thank you, sir. Am I audible?
Yeah.
Thank you so much for your session, sir. My question is related to frequency selective surface. As you, one of your slides, you have shown that reflector you have designed using frequency selective surface. So, what was the real-time challenges that you faced while designing? And also, what is the utility of FSS in next generation communication systems? Like, while if you talk about 5G and or the next generation versions of it.
Yeah, good question. So I think on the first part, I think any frequency selective surface is challenging because you have to design all the elements properly, choose the material. Sometimes when you form that as a subreflector, you have to make sure the surface is proper. Otherwise, your performance won't be correct. And on top of that, you have to thermally protect the surfaces. So you need to have thermal shield on top, a kapton, thin layer of kapton in FSS. So that is for space application. So I think future is also probably neat, but lately I'm trying to preach that get away from FSS because it is lossy component and everything you can do without FSS from the feed. Some of the slides I have shown, but some cases you need them. Like for example, 5G or aircraft, you need FSS. You cannot live without FSS. So because you have to reject certain frequencies. So you have to transmit certain frequency band, reject others. So that you can do easily with FSS. So, but other limitation with FSS is narrow band. So I can reject only certain frequencies. But if you want to reject everything, how do you do?
That's why I asked you the specific utility of FSS.
Yeah, and then you have to make multiple layers.
Uh,
So like aircraft, stealthy aircrafts, so they have multiple layers of FSS. So good question.
so
Sir, what are the parameter changes in vacuum compared to the ground level for satellites?
Yeah, I told you, I think in the vacuum, you have very big thermal changes, almost 340 degrees minus 170 to plus 170, and it's a vacuum. So there's no atmosphere there. So that means if something happens, some charges are developed. You have to either bleed the charges through some metallic structure going through grounded to the spacecraft. So otherwise you will have problem. Whereas ground, you have atmosphere, so, and space, you cannot use big dielectric materials I mentioned. Whereas on the ground, you can choose any, either dielectric material or ceramic material or metal itself. So you have a lot of choices. So designing for the space is a bit restrictive and probably more challenging because you have to uh, take care of high power, you have to take care of temperature changes, and you have to take care of the vacuum, ESV, and the PIM as well. So you don't have PIM on the ground. So Both are different. I mean, I'm not saying designing antennas on the ground is easy. It has a different complexities. Uh, for example, if you design radio astronomy on the ground, it has to withstand the wind speed, 150 miles per hour. So mechanically, it's more challenging. But yeah, antenna-wise, I think probably space is more difficult, and aircraft is also very difficult.
Sir, I have one question, sir.
Yeah,
So,
it must be a difficult one.
no, sir, it's simple only. So you have shown some bunker antenna and also some novel kind of antenna for vehicular application. Actually, those antennas shapes are actually unconventional. Actually, in that, if that is the case, how do we start our design? Some random design start with a simulation or maybe any other method, as you told,
Well,
for sector
yeah.
thing, you have used some different technology.
Yeah, I think that's where I think the experience comes into. Sometimes you get this, especially bunker antenna. I think other divisions were doing almost 1 year, and they couldn't meet the specs. So finally, they found Air Force asked them to contact me, and they came to me, and these are the applications. So can we design antenna? So actually, the other divisions are making phase arrays, and they're trying to use the amplitude and phase weightings to create a broader beam, omni-type beam, but more expensive, more costly, and dissipation is more than 1 kilowatt. And on a ground soldier, small soldier cannot take 1 kilowatt of dissipation. So then we sort of look into the application where you have to find out what is key constraints. Key constraints in this case is size, mass, and coverage, and cost. So you have to make it cheaper, you have to make it compact, you have to make it lighter, and you have to make it cheap. So what we choose is we looked into, for the bunker antenna, for example, we looked into two configurations. One is IFA, inverted F antenna, because that gives broadband also is important in this case. That's a broadband performance and very compact, right? So we choose that one, and then other one is biconical antenna. So basically, biconical also provides wide angle depending upon the biconical angle. So we kept the angle 0 so that the aperture is very small. It gives a very broad beams. And the challenge here was not the antenna, but how to deploy between the two states. So we are lying down and standing, and also how to make the white coverage for readings. So we have to choose the proper backup structure to support the antenna. So that's a non-metallic. So we gone through. Of course, we know that metal won't work. So we started right from the beginning, going through dielectric material and what is available and what is. So I think we finished the design in probably 2 months, and then we fabbed another 2 months. 5 months, I think we finished short to the customer. So sometimes you have to look into the application. So what customer is interested in. So if you can't capture that and try to design antenna by yourself, then customer won't be satisfied. So you have to know the customer and what the parameters are important for him. So different customers have different preferences. So sometimes performance is important for satellite, for example, so you have to look into that. So any other questions? Yep.
Sir, can you tell me about the career in Northrop and how we can apply there?
Career in Northrop is a bit tricky because you have to be a US person. At least you have to have a green card. So what people do normally is they graduate or do PhD here, come as postdoc and work for an year or two, and apply for a green card. And once they get the green card, I think they can apply for Northrop Grumman or any defense company. But most of them, for example, on B2, B-21 bomber and the missile program, you have to be a citizen. So once you have a green card, another 4 years, you have to, 5 years, you have to wait till you get citizenship. So what people do is work in different companies, and then once they get their citizenship, they come and join any defense company like Northrop or Boeing or Lockheed Martin. So, but directly, I think, because it's all defense related, so they don't take any foreigners.
Okay, sir. Thank you.
But you have a path slowly. You can do postdoc and
Yes.
do some good research and then work in a private company. There are a lot of private companies that are hiring, especially students from India, China, and other places. So it's a you can look into that.
Thank you, sir.
So thank you very much, sir, for your informative lecture. So as a token of love from our institute, I would like to present a memento to Dr. Sudhakar Rao, sir. Good afternoon, one and all. It's my privilege to propose a vote of thanks. First of all, I would like to thank IEEE APS Matters Chapter Chairman Dr. Shanmuganathan for supporting us to conduct this DL program at our institute. I thank our student branch counselor Dr. Venkata for her excellent support. I thank our department HOD Dr. Muthuswaminathan for extending his great support for organizing this kind of many events in our department. I extend that faculty members Professor Shiram Kumar sir and Dr. Hemant Kumar for attending this function. And also the most important person, the today's speaker, Dr. Sudhakar Rao sir, in spite of his various busy schedule, for the last 1 month, he is traveling all around India and delivering this kind of technical talk in various institutes. So on the way to Kerala, he readily agreed to come to our institute and interact with our students. So thank you very much, sir. And also the most important, the research scholars and student participants, you very well interacted with the speaker. Hope you get a lot of useful information out of his talk and you bring back this to your the future research or study whenever you go. So thank you very much. And also I extend that student volunteers of student branch of NITT as well as the MTT student branch, Mr. Birdhan, Gautam Reddy, and Sainath and other who are indirectly and directly supporting this program. And also I extend my sincere thanks to CSC HOD Dr. Bhaskar sir and his team for providing so wonderful AV support for online streaming this event. So thank you very much. So thank you one and all again. So thank you. So refreshment is available. So while going, you please have it. So before leaving, we can take a group photo. So please come forward to the stage.